Well, hello again, everybody. Well, it's a really windy day in the UK. I think we've got the tail end of some tropical storm that's recently been buggering around in America, and yeah, we've got the tail end of it now. So yeah, it's blowing really hard. My wife could learn a lot from that. I don't really do unboxing videos, but I got this delivered last week, so let's do a quick one. There you go. Oh, go on then. I know how much you guys enjoy looking at my junk. I think that means something altogether different in America, doesn't it? Well, a few weeks ago, is it that long ago? Yeah, it is a few weeks ago. I was messing around with that CRT unit. Well, floundering is a better description because, let's face it, I had no idea what I was doing. But it even goes to show that even an idiot like me can repair a logic analyzer, quite a high-tech logic analyzer, especially if it just comes down to switching boards out. But you know, when you get a chance to catch the low-hanging fruit, as it were, you might as well go for it. I don't know if everybody's been following Simon's video where, God, Simon, you do enjoy torturing yourself, don't you? I mean, I guess when you've got it all done, you must feel fantastic, but the pain you put yourself through, oh God. Well, good luck with your DSA, Simon, good luck. Because he's really been going through the mill with it. So yeah, stop watching me, go and watch Simon. Right, okay, so we were messing around with our CRT last week, weren't we? And yeah, floundering. And I was trying to measure the HT voltage to the tube, and what I did find was, yeah, this kind of thing. Actually it says Sinclair Electronics London. I wonder if it was actually made by Sinclair, the man himself, or is that just, you know, something he would have imported. I'm guessing we've got the right place because it's Cambridge, that's where he was based. So yeah, did Sir Sinclair of the C5, did he actually build this? I don't know. Anyway, it's been up in the garage for some years, and you know, who knows how good it is. You know, probably all the mice and rats have been vomiting on it for the last 10 years, and yeah, it definitely smells a little bit mousy. So yeah, I don't exactly know if we can trust that. So yeah, obviously feeling flash with money, I was actually a bit depressed and just needed to spend some money to cheer myself up. So I bought one of these, and I actually think this was actually imported from the United States, because in fact it says here, made for, oh, it says for, so not by. It was made for BK Precision. Anyway, it came from, where's that? Is that Savvy? 22820 Savvy Ranch Parkway, Yorba Linda, CA. Is that California, CA? CA? Oh, I don't know. No idea. And it's made for BK Precision. So, yeah, made for BK Precision. That doesn't sound quite so good, does it, as made by BK Precision? Yeah, so it's got an input impedance of 1000 megohm, and we've got a 1000 to 1 voltage divider. Obviously, that's some technical term of a voltage divider that I was previously unaware of. Oh dear, this just doesn't get any better. And apparently it's compatible with massed 10 megohm digital multimeters. I can imagine some little China, well, it's not China, it's Taiwan, isn't it? There's some little guy sat here at some crap old keyboard, and whenever he pressed is oh, we got an A, or I suppose an A and an O could be easily confused, couldn't it? So we've got 1000 to 1 voltage divider, and it's compatible with massed 10 megohm multimeters. Yeah. So maybe they're a special type of meter that you use on boats. Yeah, that's what he must have meant. Before applying power to this instrument, read and understand the safety whatever. Do not use this instrument in an electrical environment with a higher category rating than what is specified in this manual for this instrument. Do not operate the instrument in the presence of flammable gases. Well, there could be quite a lot of flammable gases depending on what I've had for dinner, because let me tell you, I am a vegetarian and it can probably get quite explosive in here. So don't operate in the presence of noxious or corrosive or flammable fumes, gases, vapours, chemicals, finely divided particles. Yeah, dust explosions. I used to work in flour milling, used great dust explosions there. think one of the biggest industrial disasters after all that stuff at Bhopal, wasn't it? A custard factory in America. They had a big explosion, didn't they? Yeah, I used to do a lot of work with explosion panels in mills and things like that. Big panels that are designed to blow off the roof and let the pressure vent to the atmosphere as opposed to blowing your building up. Right, okay. Yeah, boring, 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 boring. Yeah, boring, boring, servicing, boring. Boring, specification 1 kV to 40 kV. Boring. Boring. So it comes with some little toys. What does it come with? Any ideas? Strange, I've just got interrupted by my wife there, who's told me that she's just gone outside to shut the chickens up, and we was watching a cat today in the garden that we hadn't seen before, and yeah, she's just opened up the nesting box, and the cat's asleep with all the chickens. We've got no idea where this cat comes from or who it belongs to. It has got a collar on, but it's definitely a little bit scrawny, and yeah. So yeah, so now we were in, what do we do with a cat in the chicken's nest box? These are just, you know, things that I have to deal with on a daily basis. Anyway, so what's that? Well, I can tell what that is. I mean, yeah, I mean obviously that screws on there, and I guess that's quite handy if you want to hook it onto something as opposed to use the pointy proddy thing. So I guess you can hook that onto a buzz bar or something. I'm guessing it is supplied by BK Precision. They are a reputable company, so yeah, it should be good. Yeah, I wonder what this other thing's for. I mean, whatever it is fits on there, and you can also have a. I'm guessing that, you know, I'm just guessing now. I've got no idea. So you can put that thing on, perhaps. Have I got that right? I've got no idea. Yeah. Oh, I wonder if that's designed to slide under top caps. I bet. Oh, yeah, that's what that's going to be for, isn't it? Yeah. I mean, it doesn't explain any of this in the manual, but I bet that piece of bent metal with its little semicircle at the end there, you can see that. I bet you slide that under the top cap on a CRT to take a voltage measurement. Yeah, that'll be it. So obviously this one had a meter on it, but as I say, I'm just conscious. I don't know if this meter's any good or trustworthy. It seemed to be measuring about, or displaying about 10,000 volts when we were playing with that other 9-inch CRT. And I would have thought that 10,000 volts is actually quite low for a colour TV. And actually, even though it's a small 9-inch tube, I would have thought it would be a lot higher than that. So it made me think it was suspect, but I've actually got no idea what the HT voltage should have been. So, yeah. So this probe, so this high voltage probe, it's designed to be used with, oh, they're touch-proof things as well, aren't they? It's designed to be used with a meter like this, and I'm not sure, but I'm guessing that this fluke meter has a nominal 10 megohm input impedance. That's what we're expecting. And what you would do is you would connect this up like this. Importantly, you need to put your ground connection onto the chassis for whatever piece of high voltage equipment you're testing. And I think we said, didn't it? It was a divide by 1,000. So basically, whatever number we get indicated on here, we multiply that by 1,000, and that's our voltage. Now, I can only think that what we should do is, the only thing I've got to hand that can probably generate a high voltage, apart from them horrible stun gun things, is an insulation resistance meter. So let's see if I can find that. So let's give it a try. So press the button and let's put it on volts. $628. So 0.6 volts, this is indicating 0.6 volts, so we times 0.6 by 1000, so that would be indicating 628 volts. And we can just give that a try on the 1000 volt setting. And we're reading 1.2 volts, so you know, so this is telling me that, so that's 1200 volts, isn't it? So yeah, it appears that this, well, I can't tell really, can we? Is this thing producing more than 1000 volts? I'm guessing that these things probably always err on the side of caution, and in theory will produce more output voltage than they actually need, because obviously it wouldn't pass the standard if they produce less. That wouldn't be safe. So I suspect the voltage from this is a little bit higher. Unfortunately, I haven't really got a meter that we can test with it. I guess the basic accuracy of the fluke meter without the probe is obviously going to be better than having this attenuator in circuit. So what we'll do is we will risk my wonderful fluke meter by plugging it directly into the insulation resistance meter, but we're back on the 500 volts range, so let's try that. We got that plugged in right. It's reading a residual 4 volts at the moment. So I don't know if this is a good idea or not, but let's face it, I wanted a new fluke meter anyway, so let's try that. 621 volts. Alright though, so that does confirm it. Then this thing is reading a little bit high, isn't it? Oh sorry, the output voltage from this is from the mega tester is actually high. It says it's 500, but it's actually nearer to 621 volts. And I think the test probe, the voltage divider probe, the high voltage divider probe we had in, was that 628 volts or something. So yeah, they're in the ballpark. You know, what's 8 volts here or there when you're at 600 volts? And interestingly enough, we can actually see that when we were using the meter before, I'm pretty sure it was going to infinity, whereas now it's measuring 781 megohm. So I'm guessing the input impedance of this meter, this old Sinclair unit, is a little bit less than our new BK high voltage probe. I don't know if that's a good thing or a bad thing. You know, you might want a little bit of load when you're testing a CRT, I'm not sure. I can see on here they have given us a little indication knob there of maybe where the HT should be. It's got a little pointer at the 25 kV mark. But yeah, the needle on it really barely twitches. I mean, it's actually, if anything, reading low. So it's not even gone up to 1 division. So that makes me think that that, you know, the HT that we measured on those displays on that logic analyzer display, the CRT module, when we measured the HT on that when we repaired it, this was indicating about 10 kV. So I suspect that this meter was reading low and the actual voltage was probably a lot higher. Well, the CRTs were working, and that's the acid test, isn't it? Well, last time we were looking at the clocks, and I'm not sure if we had a look at this maker's label inside. But this gives you an example of how the equipment is set up. So you can see that there's a master clock here, like the one we've got in the corner that we looked at last week. And then, well, I'm not sure which one is the actual timer unit, the programmable timer. I'm guessing it might be this square box that it's got here. So you can see that you've got one master clock, and then you've got all these slave clocks which would be dotted around your building, you know, in different rooms and different offices, or even different orifices maybe. We have a floaty boat there, a Freudian slip. Well, as I said last time, I don't think I've ever had the pendulum for this clock. I bought it many years ago and kind of just screwed it to the wall as an ornament, and you know, I've never had it running as anger, and I don't remember having it. But it does make me wonder, you know, how you would fit the pendulum onto the clock. Off the top of my head, I think I looked it up last week, and the pendulum is, usually made from a piece of cast iron, and I think that it's normally about 3 inches wide by, I don't know if it's 13 inches long, and as I say, it weighs 16 pounds, which is quite a lot of weight. And that's really one of the main reasons I don't have a pendulum installed on it, because this wall that it's fixed to is only, like a stud plasterboard wall. The way my house is, it's constructed from stone, and the stone was so rough, it's got effectively, plasterboard battened onto the rough stonework. But the actual stonework is, it's more than a foot away. I once drilled a hole through the wall, and I think I had a foot-long drill, and I still didn't hit the actual stone. It's just filled with rock wool and insulation and stuff. Anyway, so what I was trying to say is that it's just mounted onto a plasterboard wall, and I didn't think that the fixings could take the weight of a 16-pound pendulum, so I've never bothered to fit one. But I would be interested to know what the procedure is for actually fitting the pendulum, because what really concerns me is if you're trying to heft this pendulum with a bob weight on it, if you're trying to heft this thing round and install it in the clock, I think you would stand a really good chance of damaging some of the mechanism. So the pendulum with its 16-pound bob weight is just really suspended from these two screws here, and then you've got a strip of spring steel here, and that kind of forms a hinge to let the pendulum pivot from one side to another, and it kind of makes you think how much stress must be on this very, very thin piece of metal here, because it looks like it's what would that be? Looks as though it's maybe about 1/2 inch wide. I'm going to do it in old money, 1/2 inch wide. I don't know what the thickness of it is, but it kind of looks like the the thickness of a feeler gauge you might use. Certainly it's a lot thinner than the gap you'd use for setting up your spark plugs or something like that. God, not many people will remember how to set up spark plugs, would they? Well, we used to have to do it back in the day. So yeah, it just looks like a thin strip, looks like a feeler gauge, and that's just clamped between these two pieces of brass, and then the pendulum with its bob weight at the very bottom is all suspended from there. I used to know what they used to call these parts here. Clock people will know what they're called, but basically that piece of metal there has a name. For some reason I keep wanting to call it a fish or something, but no, I don't know. I forget what the name is. I know Joe will know the answer to that. He knows all these words. So Joe, tell me what it's called, because I've forgotten, mate. Yeah, but my concern is you're going to have to try and lift this pendulum with its bob weight, and you're going to have to lift it onto this suspension point. So I can imagine it must be really quite difficult to actually install the pendulum in this clock, because on the pendulum shaft here you've got other bits of gubbins, mechanisms which are quite kind of delicate, especially this little thing which drags this little wheel around with every swing of the pendulum. And if you've got a 16-pound bob weight bobbing around, I would have thought you stand a really good chance of just losing control of it as you're trying to install it and bending something or doing some damage. Now I can see that, again, I don't know what the name of this device is either. It looks as though it's fixed on with a screw there. So I wonder if the procedure is to actually drop this thing out of the way while you're hanging the pendulum, and then maybe you adjust it back off afterwards. But if you know what the procedure is for installing one of these pendulums, I would, I'd love to know for future reference. I mean, I said last time, I think I might have a go at making a pendulum, but I don't think I'm going to put a 16-pound one on it. I should really check to see what the timing's like, shouldn't I? Because at the moment it's got no pendulum on it at all, and well, it seems to be timing. Maybe we'll do that. Okay, we just started that running, so we started it running at 20 past, so yeah, let's just leave it running for a little while and go and do something else. Well, the other thing I kept doing last week, I kept calling this a clock, and it's not really true to call it a clock, is it? I mean, the clock is the thing that's hung on the wall, and this is actually just a programmable timer. Now, we've actually got this thing connected up to the clock now, and I think we explained how it works last time, that about every 30 seconds the master clock on the wall produces a pulse, and that pulse pulls this solenoid in, which makes through an arrangement of gears, it makes the wheel turn, and there's these various pegs that are installed at various locations. These pegs hit these limit switches, and you can program it with effectively, I wouldn't say 7 days a week. I think it's basically designed to work, it looks like it's designed to work Monday to Friday, and then it's got some cutouts in the wheels here which I think defeat the timer for the weekend. So this is the sort of thing you'd have in your factory, telling people to come and start the slavery of work, and then yeah, bugger off home at the end of the day. So yeah, that's what this is, and it's actually running from the master clock now. We've actually all got it. We've got the cable in here, and this is just connected in. Well, the solenoid here is connected in series with the supply to the master clock. So I think you just saw it happen. Then the master clock did its thing. 30 seconds, produced a current pulse. That caused this solenoid to pull in, and the wheel whirled round. Anyway, I'll bring you in so you can have a look at that operating and see a few clicks. I think you can see as it's ticking round, it's actually cocking what we said was this one-shot timer here, this mercury vial that's got the contacts in it. And you can see that this cogwheel actually presses on it, and every time it clicks round it tilts it up a little bit, and then it's going to drop it. So let's have a look at that happening again. So this little edge has really moved on to the flat part of this tooth now, so I think this is kind of primed, ready to go. It's not going to drop. We've got to wait for this edge here. This trailing edge is just going to pass this, and when this trailing edge passes it, it's going to drop this. Is it going to drop on the next tick? It might do. Let's see. There we go. And you can see that the mercury ran forward and then it drained away into this, well, into this separate chamber. And that would have produced a 7 or 8 second pulse, which would have been the, you know, your alarm or your bell going off for your factory to tell everybody to come in, or again to bugger off home at the end of the day. I think let's just install one of these pins here. So this pin is just starting to make contact here. It's just going to pick up on this ramp, and what it's going to do, it's going to close this limit switch, and that's what would trigger our bell. So it just moved up a little bit more there. I think I said earlier there's 2 sets of switches. You've got the set at the front here and another set at the back behind it. And the front set says Monday to Friday on it, and then the back set says Saturday, Sunday. Well, our switch contacts are nearly closed. They're not quite. Oh, yep, I think that kick has just closed them now. So these contacts are now going to stay closed, but the little mercury container we looked at earlier, it's not quite ready to trip yet, so I don't think our alarm would have been sounding. So surprisingly, it's still continuing to press this switch hard on. I don't think it's going any more on, but the actual the lever that presses on this bar now, I think it's about halfway off this bar, but you know, halfway around the circumference of it. So I would have thought that in the next few clicks, this this switch is going to fall off. Sorry, this little piece of brass here is going to fall off the pin which is triggering the switch, and that'll cause the switch to open. But I'm thinking it's not before the little mercury vial's done its trick and drop down and give us the 8 second alarm. So let's go back and watch the mercury drop. There we go, that limit switch just released there. So we went through a bit of a cycle there. That's the alarm cycle. Now that mercury timer isn't actually going to be any use to us when it comes to making my cup of tea in the morning, because it takes more than 8 seconds for the kettle to boil. So I guess we're going to have to short that out, aren't we? So we've got the supply here coming into the timing circuit, and this resistor is in series with the 0 volts connection. And I put a 1 ohm resistor in there because what I'd quite like to just have a look at is the actual the clock pulse, the synchronization pulse that drives everything. Because we're going to have a go at replicating the master clock, but using some solid state electronics. So before we do that, I just thought it would be just a good idea to characterize the the pulse that actually comes from the real clock. So let's do that. So we've got this resistor installed in series with the power supply that's going to both the actual master clock and also this slave programmable timer. And what I want to do is I want to characterize this pulse that we're getting every 30 seconds. So what I can do with this resistor, basically, we're going to get a current pulse every 30 seconds, and we can connect the oscilloscope just across this resistor, and you know, we can defer from the voltage change across the resistor what the current is, and we can also do things like look at the timing for that pulse. I'm guessing it's going to look pretty horrible actually. I'm quite excited to have a look at that. So let's switch the scope on and connect up some crow probes. Now often you do have to be just a little bit careful when you're taking measurements like this, because if you're not careful you could very easily connect your scope probe to the wrong side of your power supply. Now it isn't actually going to matter very much for what I'm doing here today, because the power supply that I'm using, it isn't referenced to ground, everything's floating. But yeah, you could have problems, and yeah, I've actually got the resistor installed in the 0-volt line. And for everybody playing along at home today, we're using the Keysight DSO 32024T, and we've got that set up to have the normal coupling for the trigger mode, and we've got it set to do a single sweep. Oh, and there we go. So let's just center that a little bit better on our display, and we'll also just turn the attenuation down a little bit. Or rather, should be turning it up a little bit more actually. So what have we got? We're on 10 millivolts per division, and we've got 1, 2, 3, 3.5, let's call it 3.5 divisions, so that's 35 millivolts. V over R equals I. So we said we've got 35 millivolts, and our R is 1 ohm. And actually those are quite nice numbers, don't they? They work out quite nicely. We don't have to do any hard maths. We can just literally turn the millivolts into milliamps. So we've got a little bit of a peak current there of 35 milliamps. I actually think that's quite interesting. It actually tells you in the clock setup information that the I think the ideal current, it says, is 22 milliamps. But I'm sure that that would have been measured with some old AVO meter or something like that, and probably wasn't particularly accurate. So I think 35 milliamps of drive is going to be fine. It's not going to hurt anything. So let's have a look at some other characteristics of our clock pulse. Is it me, or is there another little spike there? Is that a real thing? That's quite interesting. I suspect it is real. Let's look at that little... Oh, yeah, look at that, quite interesting. Got a little spiky there. And there's another one at the other side, isn't there? So you've got to remember that really these electromagnets, these coils, basically what they really are is huge inductors. So we can actually probably see what the little resonant frequency of our circuit is there, because it's probably got a resonant frequency. The scope timing isn't really set up perfectly to do that. No, oh well. But you can see all this switching nastiness here as the inductor dumps all the energy that it's stored. It's trying, go away. It's trying to maintain the current across the inductor, because that's what that's what inductors do when you open circuit them. So of course, to try and maintain the same current, the only thing it can change is the voltage. So you get these voltage spikes, and you'll find that there's some resonance there to do with the capacitance of the well, mainly because of the inductance of the coil that we use in our solenoid coils, but they've also got self-capacitance, and it forms a little RC resonance circuit. Yeah, waffle, rubbish, blah. Come on, where have you gone? Where have you gone? Come on, pulsey, pulsey. Interesting that we've got this little bit of a humpback pulse here, and I wonder, I've got no idea, but I wonder if we're getting that shape because we've actually got two inductors in circuit. Well, we've actually got three, because we've got the coil which is actually pushing the pendulum along in the master clock. The actual master clock has also got a a solenoid in it to actually make the hands go round on the front, and then we've got a solenoid in the slave unit, and we're actually seeing the kind of the summation of all those currents. They're all going to be slightly out of phase with each other. So yeah, that's quite interesting. That. So I wonder if one of these little pulses here is from the master clock and the other is from the slave. And I wonder which one's dominant. Yeah, I'm not sure, but that's interesting as well. Right, okay, waffling. So how do we measure that? I can never remember I use this thing. There we go. We need some measures, don't we? Measures. Measure. Is that a measure? Is it measures or cursors? Where's the button that says cursors on it? There's a cursor button somewhere. Cursors, there we go. Cursors. X1. You know what, I can't even remember how to work them bloody cursors, so let's do it the old-fashioned way. So we're set to 20 milliseconds per division. Let's just line that up a little bit. God, I'm useless, aren't I? It's probably bloody easier anyway. 20 milliseconds per division. 1, 2, 3, 4, 5, 6, 7. 7 times 20 is 140 milliseconds. So a very simplified view of our pulse here. In that basically our master clock is giving us 140 milliseconds wide pulse, and the maximum current that we reached here, as we said, which is basically there, was 35 milliamps. So when we build our little electronic timing circuit to take the place of the master clock with its big fudding pendulum slapping around the joint, we need to produce a circuit that every 30 seconds is going to produce a 35 milliamp current pulse, which is 140 milliseconds wide. Oh, in the ballpark, I'm sure it doesn't matter that much. Okay, we've been going 52 minutes there, and I missed it, the exact timing, but it was just over 52 minutes. Let's call it 52 minutes 10 seconds. And in 52 minutes 10 seconds, our actual hand on the clock here has gone round 1 hour, because it started at the 20 past mark, and it's gone all the way around. So this clock is obviously every hour at the moment with no pendulum fitted. It's running 8 minutes fast, which I actually think is pretty surprising, considering it has got no bob weight on it. So yeah, quite surprised about that. Maybe those arrow buttons do something, do they? Oh God, no! What's happening now? No, stop that! What are you doing? It's gone. You can see here the hallmarks of a true professional. I've got quite big fingers. What I thought you had to do, I thought that basically when you highlighted the cursor there, I thought that you could then, this soft key becomes active, and I thought that you could actually turn that to actually move these cursors along, but they're not moving. It's bringing up another menu. So I don't know what I'm doing wrong. So basically what you can do is you've got to pick these things up and you've got to move them, but if you've got big fingers like I have, they're just really, I see, it just does bloody menus and everything else. Cool. Well, why won't you move? Oh God. Is that it? Is that, oh God. No. No, what are you doing now? I don't want to puss anything. I don't want to annotate anything. Stop. I don't want to annotate. Cursors again, please. Oh, let's try automatic. Does that do anything? No. God, how do I tap or... I don't want you to annotate. Stop bloody annotating, whatever you're doing. Can I move it over there? Alright, okay. Delta X, 138 milliseconds.